Let's look at z-scores. So what's the purpose of a z-score? So the reason we need z-scores is when we're comparing two different sets of data. So in this case, we have two different races going on, and we want to see who had the more convincing victory. So we have the Indy 500 and the Indy Grand Prix, and we have two drivers who finished, and we want to see who finished in basically in a better time, who had the more convincing victory. So let's look at this and see who had the more convincing victory. So to do that, we want to look at their z-scores. So I'm going to put a table here again. And write down some important information here. So we have a couple of things going on. We have our mean, and then our standard deviation, and then the winning car. And then we have, like I said, the Indy 500 and the Grand Prix. So it says that the Indy 500 here, the mean was 186.15 minutes, and the standard deviation was 0.359 minutes. And we have the winning car there, Dario, who finished in 185.62 minutes. So let's fill that into our table here. So our mean is 186.15. Our standard deviation is 0.359. And then our winning car is 185.62. And that is Darian. So I'm going to keep his name down there. So then we have the Grand Prix here. And we have that the mean is 112.8 minutes, and the standard deviation is 0.131 minute, and we have Will Power, who finished in 112.57 minutes. So you can see a little bit different of things going on with those two races, and that's why we need to look at their z-scores to compare how far away they actually were from the mean. So our mean here is 112.8, and the standard deviation is 0.131 minute, and then his score was his time was 112.57. So let's look at their z-scores. So let's recall what a z-score is. So z-score is the data values, in this case x, minus the mean. So these are all the drivers, so I'm going to use population. So minus the mean over the standard deviation. So we have two drivers going on here. So you have Daria and then Will. So I'm going to use z sub d to represent Dario's z-score. So his is going to be 185.62 minus the mean, divided by the standard deviation here. So there's two ways to do this. Is you can break it down and look at the numerator first. So let's do it this way. So 185.62 minus 185. 186.15. That's negative because you finished before the mean time, right? And then divide that here. So then we're going to just divide that by 0.359. And then let's round that 2 places. We usually round z-scores to 2 decimal places. And you'll see why later on in this course. Right? The other way to do is we can type this in at one time in the calculator. To do that, we need to type the numerator in parentheses. So 185.62 minus 186.15. Close my parentheses because I want to calculate the numerator first. Divided by 0.359. Enter. We'll get the same answer. So let's look at Will Powers. So z-score, and I'm going to use W for Will Powers. So we're going to take his finish time and then subtract the mean and then divide it by our standard deviation here of 0.131. So let's just do this all at one time. So 112.57 minus 112.8, close my parenthesis, divided by 0.131. And we know we should get a negative value since he finished before the mean time. So his is negative 1.76. So let's think about those values there. So what does z-scores represent? That tells us how far we are away from the mean. So this is telling us that Will Power is more standard deviations below the mean, which is what we want, because remember, if we're finishing more standard deviations below the mean, we're finishing in a faster time, right? So these problems, you want to pay really close attention to the context of the problem. So let's type our answer here. So we have that Will Power had the more convincing victory since his z-score was smaller. Remember that the larger the negative value, so the larger the number actually is, so that 1.76 is a bigger number than 1.48, but it's smaller because it's negative. So it's smaller, meaning he was more standard deviations below the mean, which means he was relatively faster, right? So you want to keep that in mind there. So sometimes your problems are going to ask for more convincing victory, or if somebody weighed more or less, or so you want to pay really close attention to the problems, and if you're doing similar exercises, it may switch on you from problem to problem. So with that being said, let's look at another example. So you have the mean height of males here, and then the mean height and the standard deviation for females, and we want to know if Kevin or Candace is relatively taller. Right. So let's compute their z-scores here. So we have the z-score of Kevin. So that's going to be the data value, so his height, minus the mean, so mean height of males, divided by their standard deviation. So let's go ahead and compute that. So parenthesis 83 minus 69.1, close my parenthesis, divided by 2.8. So that's approximately 4.96. So way above the mean. We're looking in that rare percent. So remember that if it's approximately bell shape here, that there's 99.7% that lie within 3 standard deviations. So he's in that rare percentage there. Now let's look at Candace's z-score. So her height is 76. The mean for females is 63.7, and then divided by our standard deviation of 2.7 there. So we have 76 minus 63.7 divided by 2.7. So just a little bit smaller here. Still both extremely large. So what can we say here? So we have that Kevin is relatively taller since he has the larger Z-score. So that means that he's more standard deviations above the mean, right? So that means that he's taller there. So just make sure you're reading these problems really carefully. It may have asked who was relatively shorter, and both of those are extremely tall in context, but be careful with the wording there. They may trick you up, so just be really careful with the problems there. So that explains how to use Z-scores in problems.